In this video, I will go through the Unit 3 review for pre-calculus on the portion of the test where the calculator is allowed. As a general rule, round all of your answers to 3 decimal places unless it makes sense to do something different. Right, so we're going to solve these equations, and we want calculator accuracy, so we're going to wait till the end to use our calculator. So algebraically here, first thing we're going to do is subtract 3. Then divide by 2. Then to get rid of this exponent, what I'm going to do is raise both sides to the reciprocal exponent, so to the 4/3. We're not multiplying by 4/3, we're raising it to the 4/3. So x is going to equal 2 to the 4/3, which you just do in your calculator. Okay, and we get 520. Okay, the next one is similar. We're going to solve for x and then plug it in the calculator. So subtract 5. Then raise it to the reciprocal power. So 2x minus 1 is going to equal 5 to the 4/3. So 2x equals 5 to the 4/3 plus 1. And then we'll divide all that by 2. Okay, so carefully enter that in your calculator and you'll get about 4.775. When the base is a number and the exponent is a variable, that's where we're going to need to use logarithms. So I'm going to solve for e to the x first. So 2e to the x equals 53. So e to the x equals 53 over 2. And then we take the natural log of both sides. Natural log of e to the x is just x. Typing that in the calculator gives us 3.277. Similar problem, we'll subtract 12. Then divide by 4. Okay, at this point, once the e is by itself, we'll take the natural log of both sides. And then divide by 3. In the calculator, 0.501. We're still going to do natural log on both sides, but the natural log doesn't cancel out the 6. What it does allow us to do, though, is to take this x minus 2 and get it out of being the exponent. Okay, so I'll distribute through. So x natural log of 6 minus 2 natural log of 6 equals the natural log of 30. We want to solve for x. I'm going to add that over. And then divide by the natural log of 6. So that's solved. And we type it in the calculator. Get that. Okay, 32 is going to be similar, but we're going to have more moving parts. So I'm going to do the log of both sides. And it doesn't matter what base log you use. I just tend to use natural log. Now we've untrapped our exponents. So I'll distribute through here. So x natural log 3 plus natural log 3 equals 2x ln 4. I'll move everything with an x to one side and everything that doesn't have an x to the other side. Then I can factor the x out. Okay, then the last step to get x by itself is going to be to divide. So x will be negative natural log of 3 over natural log of 3 minus 2 natural log of 4. Three decimals is 0.656. And this one will be handled in the same way. I'm going to take the log of both sides. Which allows our exponents to hop down. Make sure to put parentheses around that whole thing. Then distribute. So I'm going to have 0.1 times x times the natural log of 8 minus 4 natural log of 8. I'm going to move the x over to this side, minus 0.1 x ln 8 is going to equal negative 4 ln 8. Factor out my x. And then divide. So my x will end up equaling negative 4 ln 8 divided by all of that. Okay, and that's a 0.1, that's an L, which I know they look the same. Type that in the calculator, you get negative 8.040. Alright, so now we're going to continue to solve exponential and logarithmic equations. It's just now they're going to be in the context of a situation. So assume that the equation of speed of a plane is given by s of t equals ce to the kt. Some people get confused with this notation and want to say that's multiplication, but that's really just saying like f of x equals ce to the kx. It's just function notation with different variables. So this is just our general exponential equation base formula. C is always going to be our initial condition because when time is 0, that piece goes away. So in this, our initial condition at time 0, we're at 400, and at time 40, we're going 500 miles per hour. So this is what we're going to use. I'm going to plug 500 equals 400 e to the k times 40. And that'll be pretty consistent with our problems. Then I'll divide. Then we'll take the natural log of both sides. So natural log, I'm going to make that just 5/4 equals natural log e to the 40k is 40k. So my k is the natural log of 5 over 4 over 40. So that's going to be 0.00558. So my general equation, s of t, the speed of our plane, is 400 e to the 0.00558 t. Okay, that's the answer we're looking for when asked for a general equation. Now we're going to use that general equation to find out when the plane reaches 750 miles an hour, the speed of sound. So we'll just set it equal to 750. And solve for t. So we'll divide. take the natural log, and then divide. So we're going to get 112.6 seconds. And rounding to the nearest tenth there is fine, or you can do 3 to be safe. All right, our next problem, Phoebe is returning to Earth in her spaceship when she detects an oxygen tank leak. The pressure in the tank is given by, and again, this is just function notation, so the pressure in terms of time is just our basic exponential guy there. The initial pressure, so when t equals 0, our pressure is 3,000 psi at time 0. 5 hours later, so t equals 5, the pressure is at 2,300. At that time, 5 hours into the trip, Phoebe is still 18 hours away from Earth. Will she make it home before the pressure drops to 800 psi? All right, so we're going to do basically the same thing we did in the last problem with different numbers. So we're going to set our equation equal to 2,300. Our initial value is 3,000. E, we're trying to find K. Our time is 5. So doing that algebra for the 100th time, natural log of 23 over 30, that divided by 5 gives us negative 0.0531, because this is exponential decay. So my general equation, P of t, is going to be 3,000 e to the negative 0.0531 t. Now you could use the 2300 as your initial condition, and that's just going to change what value we plug in for the next part. So for the next part, she's still 18 hours away. So will she make it home before she presses 800? So you could set this equal to 800 and solve for the time, or we can take the time, which is going to be 5 plus 18, and see if the pressure is greater or less than 800. Okay, so if we do that, we get 886.577. Okay, which is greater than 800. So yes, she will make it home before the pressure drops to 800. On the next page of your review, you have two Newton law of heating and cooling. I'm just going to go through one of them. I'm going to go through the second one. All right. Every day, Mrs. Benson, my daughter, wants macaroni and cheese for lunch. After microwaving it, it's too hot for her to eat. So I put it in the freezer to cool down. The macaroni and cheese is 200 degrees Fahrenheit when it is first out of the microwave. The freezer's temperature is 2 degrees Fahrenheit. After 5 minutes, the macaroni has cooled to 180 degrees Fahrenheit. Using Newton's law of heating and cooling, when will the macaroni be safe for eating, the safe eating temperature of 100 degrees? All right, we're going to find A, K, C in the general equation and then solve the problem. So remember, C is our surrounding temperature. And A is the initial temperature minus the surrounding temperature. So in this problem, my surrounding temperature is the temperature of the freezer, which is 2. My A is going to be the initial temperature of 200 minus the surrounding temperature of 2. So this will be 198. To find K, we're going to use the fact that after 5 minutes, our temperature is now 180. So I'm going to set my equation equal to 180. My A is 198, e to the K times 5 plus C, which is 2. So I'm going to subtract 2. Divide. Take the natural log. Okay, and then divide. So our K in this scenario is going to be negative 0.0213 because our temperature is decreasing. Okay, so then I can make my general equation. T is going to equal 198 e to the negative 0.0213 t plus 2. And we want to know how long it's going to take before my daughter can eat her macaroni. Okay, so we'll solve this equation. So 98 equals 198 e to the negative 0.0213 t. Divide. Natural log. And finally divide. Okay, and it's going to take us 33 minutes before we can eat our macaroni. All right, our last problem. A common statement is that there is 1 rat per person in New York City. Below is a fictional table of data regarding the number of rats in thousands of the city in a given year. And we're going to find a logistic model for the data. So before I enter this in, I'm going to adjust these numbers. I'm just going to make that 40, 50, 60, and so on when I enter it into my table. So we go to Stat, Edit. If there's something in there, you're going to clear it. Now, it was the data that I just needed, but we're going to enter the years into our X's. And 100. Okay, then we put in our rats. So once we have entered the data in here, we are told to make a logistic model. Okay, so then we go to Stat, over to Calc, and we have all our different regressions that we can run. We want to run a logistic regression. List 1, list 2, I'm going to go ahead and store it in Y1 because we're going to use it in the second part. Then we'll calculate. Okay, it gives you the general equation, and then it gives you the values that we're going to plug in here. So my general equation, we're going to have y equals, okay, logistic has a big fraction bar. C is on top, so 229.962 is on top. On the bottom is 1 plus, our A is 502.789. E is the number E. To the negative B is 0.1 times X. So that's our logistic equation to model this data. For this one, our follow-up, a better estimate is that there's about 1 rat per 36 people. The estimated population of New York in 2007 was about 8.3 million. So how close will this match the perhaps actual number? Well, let's figure out from this. Okay, if we have 83 million, or 8.3 million, and we divide that by 36, we get about 230,555 grads. So now we're going to look at our logistic equation and see how close we were in 2007. So we're going to evaluate our function at 107, because that's how I did the, if 2000 is 100, 2007 is 107. Okay. Remember that we stored it in our y1. Okay, so that's in there, and that's why we stored it in there. So then I can just evaluate at 107. Okay, so we get 223.7. But in the chart, that's in thousands. So this is really going to be 227,410, which is actually kind of close to the 1 to 36. So that is the calculator portion of your pre-calc test review for Unit 3.